Hello everybody, welcome back to the World of STEM. This is Pranav Eada, and today we will be discussing forces, which is a key unit in the AP Physics 1 and Physics Honors curriculums. So let's dive straight in. Alright, we have forces, and forces are defined as pushes or pulls on objects. They are an interaction between two objects, which means that all forces have to be some sort of interaction. They don't stem in from the middle of nowhere. The interaction can either be through contact or with no contact, which we will see in later examples. Forces are a vector quantity, which means they have both a magnitude and a direction. So an example would be 13 newtons newtons are the units of force. So 13 newtons to the right, or negative 6 newtons south, which means 6 newtons north. So they have both the magnitude and a direction. So like I said, the SI units for forces are newtons, which are symbolized with a capital N. And the symbol for a force, like expressing a general force, is a capital F with the with an arrow on top, and the arrow on top means that it is a vector quantity. All right, let's move on to Newton's 3 laws of motion. So these are 3 fundamental laws of motion that were deduced by Isaac Newton, and they are the core of how we approach forces. So the first law is the law of inertia, which states that an object at rest remains in rest, and an object of motion remains in motion. And both cases are only broken when there's a net external force that is introduced into the system. So a block on the ground with no force would remain in position, and it's only going to move if you push it, which is applying a net external force to the block. Another point under the first law is that velocity is going to be constant when there's no net force acting. All right, let's look at the second law, which is an equation that states that the acceleration is equal to the net force over the mass. So that is net force in this situation. And this is often re-expressed as the force is equal to mass times acceleration. And so we have F with the arrow is net force, and then it is a vector sum of all forces acting on the object. Net force is the vector sum. Right. So now let's move on to the third law, which is action-reaction, which states that every action has an equal and opposite reaction. So this means that forces come in pairs, and the two forces in a pair are acting on two different objects. Another important thing in force pairs are that they are equal in magnitude, but they are opposite in direction. So if I have 6 newtons to the north, the force pair would be 6 newtons, but to the south. So equal magnitude, opposite direction. Examples are I push on the wall pushes back on me. So if we have that is the first example. And the second example, if we have a table that pushes up on a book, the force pair for that would be a book pushing down on a table. So that's our force pair here. All right. So now let's move on. So we're going to discuss non-contact and contact forces, which are the two primary type of forces. And the main type of force under non-contact force is the force of gravity. So the force of gravity is also known as the weight of an object, commonly in problems. It is a measure of the gravitational pull between a mass and a planet, usually. And it is proportional to the mass and local acceleration due to gravity. The local acceleration here means that whatever the gravity is on that specific planet. So on Earth, it's 9.81 meters per second squared, the magnitude of acceleration. But on other planets, the magnitudes are different. They're not the same as on Earth. So we use the local acceleration of gravity on the specific planet we're talking about. And in formula, this is just the force of gravity equals mass times gravity, local acceleration due to gravity. All right, so let's look at this practice problem here, which states that an alien has a mass of 120 kilograms. And we want to know what the weight of the alien is. And in part B, they give us the weight of the alien on its home planet, and we want to know what is the local acceleration due to gravity on its home planet. So for part A, we're going to have that the force of gravity equals mass times gravity. Just over there. And then with the force of gravity, which has to be the mass, which is 120 kilograms, times the local acceleration due to gravity on Earth, which is negative 9.81 meters per second squared J hat. So multiplying the two, we have our force of gravity is negative 1,177 newtons J hat. If you notice, we have given both a magnitude and a direction, which is what a vector quantity requires. So that's part A, relatively straightforward. And part B, we have the same equation, but over here, now we're solving for G. So rearranging the top equation, we have the G equals force of gravity over mass. And we're given the force of gravity as the weight, which is a magnitude of 30 newtons, but it points downward. So we have negative 30 newtons J hat, and then we're dividing that by the mass, which is 120 kilograms. So our local acceleration due to gravity on the alien's home planet would be negative 0.250 meters per second squared J hat. So that's a fundamental problem, which is relatively basic, that involves the force of gravity, but very important that you grasp this. Right, let's move right along. So now we're going to discuss contact forces. Then there's two types on this slide and one on the next slide that I'll be covering. So the first contact force we're going to look at is a tension force. A tension force is most commonly caused from a pull of a rope or cord or string, or etc., something of that sort. And usually we are given ropes and problems, so that's what we will be discussing in terms of. So key assumptions that we are making for the tension force in fundamental problems, usually in AP Physics 1 and Physics Honors, is that we have the same magnitude of the tension force throughout the rope, which means that the rope never has mass for our purposes in the problems, but usually a rope obviously does have a mass. And then we also have the normal force, which is a force between any two contact surfaces. But the direction of the normal force is always perpendicular to the surface. So it goes away from the surface and at a right angle to the surface. And then our third type of contact force is a frictional force. A frictional force is a force between two surfaces, like normal force. But this time it is actually parallel to the surface and opposing the relative motion as compared to perpendicular and away from the surface. And we always have a coefficient of friction in a frictional force. So, like I said, let's draw an example here. So if we have box A and there's a force going this way, then the frictional force is directed parallel to the surface, which is over here, but away from the motion of the object. So our frictional force is drawn like as such. And then let's look at static. There's two types of frictional forces, which are static or kinetic. Static forces are usually larger than kinetic forces, and an object needs to overcome a static force to begin moving. Only when it overcomes a static friction force can it switch to kinetic friction force. So static because the object is at rest, kinetic because it's moving. And the formula for a frictional force is that it's proportional to normal force with the constant of the coefficient of friction. So that basically means that the frictional force is mu times the normal force. Right. Let's move on to the next question here. So we have a question here, which is asking us to draw a free body diagram for an object that is being pushed to the right across a rough horizontal surface at a constant velocity. So a rough horizontal surface means that the object has to have a frictional force because the surface is rough, and at a constant velocity. If you remember earlier from the slides, that means that the acceleration of the object is zero, which means the net force in all directions is zero, which means that the magnitude of the vertical forces are equal and the magnitude of the horizontal forces are equal. So hopefully when you draw the free body diagram, it should look something like this. We should have that as our free body diagram. If you notice here, there's the box. To the right is the force applied, to the left is the frictional force, and those are equal in magnitude. And then To the top is the normal force, and to the bottom is force of gravity, and those are also equal in magnitude. And like I said, the net force in both directions is 0. There's no acceleration in both directions, which means the magnitude of all forces have to be the same. Lovely. Let's move on to the next question. So this one is regarding friction. So we have the block with the mass of 0.805 kilograms, which rests on a rough surface with mu k. Mu k is the coefficient of kinetic friction, which is 0.320, and mu s, the coefficient of static friction, is 0.450. So in the block set at rest, we're asked for the frictional force, and then part B gives us an applied force and wants to know the block's acceleration. And in part C, the applied force is reduced and it wants to know what the new acceleration of the block is. So solving part A, we want to use static friction because the box is said to be at rest. So we have the formula for frictional force as being mu times the normal force. So the normal force is just mg in the context of this problem because we have the block and we're said it's not moving in the vertical direction. So there's the force of gravity on the bottom that's acting on the box. And then so there also has to be a normal force acting on the box. So that's why, since the force of gravity equals mg and f of g equals f of n, we have that mg has to equal f of n also. Sorry, let me make that better. F of n. Right. So that's that. And so the normal force we have is the mass 0.805 times gravity 9.81, which is 7.90 newtons. And the force due to static friction here is mu of s, which is 0.450 times the normal force 7.9. We arrive at an answer of 3.56 newtons. That is the frictional force of the object. And then for part B, we have to check if, so before starting, we have to check whether applied force is greater than force of static friction or the object doesn't even move. But obviously, the applied force is 5.6 and the force due to static friction is 3.55. So that's greater. So now we switch to kinetic friction. And solving for kinetic friction, we get that it's 2.53 newtons. We're basically just using mu of k instead of mu of s. And then we know that net force is mass times acceleration. So to find the net force of the object, we have to do force applied minus force of friction in the kinetic, because force applied is going this way and then force of kinetic friction is going to go this way. So subtracting both quantities, we end up that the net force is 3.07 newtons, which means that the magnitude of the acceleration is going to be the net force over the mass, which is 3.07 newtons over 0.805 kilograms, which means our net acceleration's magnitude of the acceleration is 3.814 meters over second squared. And then part C, when the applied force is reduced to 2.8 newtons, this is a very nice question, which is tricky and can trip up most students. But as always, we're going to check whether applied force first exceeds static friction. And very clearly, 2.8 newtons is less than 3.55 newtons. So because the applied force does not even exceed static friction, we don't even have an acceleration. The block cannot even move. So for part C, the block does not move, which means acceleration is 0. So make sure you always check whether the force opposing the friction is greater than static friction before even starting the problem and transitioning to kinetic friction, because sometimes static friction is greater and the object does not even move. Alright, finally we have this diagram related question here, which says a 10 kilogram block is on a smooth horizontal table with a horizontal string, and we want to know what the magnitude of the acceleration of the 10 kilogram block is, and it's connected by a horizontal string to a 63 kilogram block that's hanging over the edge. Right, so I drew this diagram here, and we can see that there's the 10 kilogram box on the table connected to the pulley, and then the 63 kilogram box is hanging down. So in the x direction, the force, there's only a tension force over here. So the force of tension 1 is represented here through this string. And then in the y direction, we have a gravity force that's acting on this object, and also a tension force from the string that's acting. So F of G2 minus F of G2, since they act in opposite directions. And in the context of our problem, we're defining positive acceleration in the downward direction. So this box is going this way, and then this box is going that way. So the force of gravity is positive, and the force of tension is positive in this case. So we have the force of tension, which is just through Newton's second law, the net force equals ma. So the force of tension is m1 times a, since the tension force is on the mass 1, 10 kilograms. The force of G2 minus the force of tension. This force of tension is the same, is mass of 2 times a. So substituting the force of tension into this equation, we end up that F of G2 minus m1a equals m2a. Bring m1a over, we have m1a plus m2a equals m2g. m2g is basically rewriting F of G2. And so our acceleration we find through derivation is m2g divided by m1 plus m2. So in outward machines, you commonly see these setups, and you basically just have to break up the force into horizontal and vertical components, and then solve for acceleration in terms of other variables. And then we're seeing that we're given the masses, mass 1, mass 2, and then, mass 1, mass 2. So we have the acceleration in the last page, which is m2g over m1 plus m2, which is m2g m1 m2. So plugging in, we have 62 kilograms times 9.81 meters per second squared over 73 kilograms. And you should end up that the magnitude of acceleration of the system is 8.46 meters per second squared. So approximately 8.5 meters per second squared. So yes, that was basically all the problems covering the concepts that we learned today. Thank you so much for watching this video with the world of STEM. And if you have any questions, please feel free to comment down below, and we will try to do our best in answering them promptly. Or you're always free to email us, and the email will be provided in the description of the video. So thank you so much for watching again. Please consider liking, sharing, and subscribing so that we can benefit as many people as possible. And once again, this is Pranav Eada with this World of STEM signing off. Bye-bye.